How do you solve equations containing rational expressions? So here are some ideas to keep in mind as we go through the examples. First of all, when you solve any kind of equation, it doesn't matter whether it has rational expressions or not, the process always boils down to undoing operations in order to isolate the variable. The next thing we have to know is, well, what in the heck is a rational expression? A rational expression is a fraction, and it does follow all the rules that we use for working with fractions. So rational expressions can be reduced, added, subtracted, multiplied, divided. Here's an example, a couple of examples of rational expressions. Really, we're interested in fractions that have variables in the denominator. One more thing to remember about fractions is that the denominator can never be 0. Do you remember why? And do you remember how to work with just regular old fractions? If not, that's something that you might want to go back and review. We'll look at a couple of examples of how to simplify rational expressions, and then we'll move on and we'll solve equations that contain rational expressions. The basic strategy for reducing rational expressions is to factor the numerator and denominator and then divide out or cancel out all the common factors. So the first thing in this example that you'll want to do is to factor the numerator and the denominator. Now recall that when you factor, what you really do is you create a multiplication problem. And the pieces of that multiplication problem are the things that we are referring to as factors. So in this case, in the numerator, the x and the x plus 5 are factors. The next step is that we're going to divide out all the common factors. We have a factor of x in the numerator, a factor of x in the denominator. We can cancel or divide them out. And then we can go ahead and we can multiply together all our remaining factors to get our final answer, we hope, x plus 5 over x. Now, let me ask you this. Why can't we cancel out the x's at this point? Take a look at a problem that just has numbers in it. What do you think? If we canceled out the 2's in this example, 2 plus 5 over 2 equals 5 halves, would that be right? And if you said no, you're absolutely correct. In our numerator, x plus 5, x is not actually a factor because it's not a part of a multiplication problem, so you can't factor it out. All right, so finally, we have what we think is our answer, our simplified answer, x plus 5 over x, and we have to add a caveat with these kinds of problems. With rational expressions, since we have a variable in the denominator, and the denominator is not allowed to be 0 because that means that our expression is going to be undefined, we have to put a caveat to tell our audience that this x plus 5 over x is okay except for the cases where x is 0, and then this is not going to work. Now, to determine what values you have to leave out, you do have to go back up to your original expression and determine for what values of x will x squared be 0. Write another example. First thing, factor the numerator and the denominator completely, and if you want to make sure that you've remembered your factoring skills, go ahead and pause and factor. This factors x plus 2 times x minus 6 in the numerator, x plus 2 times x minus 2 in the denominator. We see that we have a factor of x plus 2 in both the numerator and denominator. We're canceling them out, dividing them out. So we are left with x minus 6 over x minus 2. The last thing we have to do is write our little caveat. Are there any values of x that are going to cause our original denominator, x squared minus 4, to equal out to 0? Well, definitely. If you plug in a negative 2 for x, then x squared minus 4 is going to be 0. And if you plug in a 2 for x, then x squared minus 4 is equal to 0. So these are the two values that we have to warn our audience about. Let's solve now. The basic strategy is to find a common denominator and multiply all the parts of the equation by the common denominator. Now, this is the same strategy that you learned when you were first working with linear equations and you wanted to clear fractions. You would multiply by the common denominator. For this problem, we can multiply all three denominators together to find a common denominator of 15x. So we take that 15x and we multiply every piece of the equation by 15x. So starting at the left, we see that the 5 and the 15 are going to reduce down to 3 over 1. We see the 15x times 1 over x is going to reduce down. And the 15x multiplied by the 2/3 is going to reduce down. So let's simplify our resulting equation. So multiplying things back together, we end up with an equation that has no fractions in it. Now, if you picked a common denominator that was incorrect, then you won't be able to make your fractions disappear. So if at this stage you still have fractions, then you know that you picked the wrong common denominator. You picked something which was in fact not a common denominator. All right. So then quickly you can just solve this. This is a linear equation. Solve it as you normally would. We get our solution, x is equal to 15/2. Now with our rational expressions, we have to make sure that our solution is not going to cause any of our fractions to be undefined. So they're not going to cause a divide by 0. Well, if we substitute that 15/2 back in for x in our original equation, we see that we're not going to get a divide by 0. So we know that we've got a valid solution. In this example, again, we're looking for a common denominator. There is only one denominator, x minus 2, so that is our common denominator. We're going to multiply every piece of our equation by that x minus 2. You can see where the x minus 2's cancel out. On the left, we have an x minus 2 in the numerator and an x minus 2 in the denominator. Those cancel or divide out. And on the right-hand side, same situation. So now we round up everything that we've got left, multiplying things back together. We see that we've cleared all the fractions. So yeah, we used an actual common denominator. Now this is a linear equation. Solve it as you normally would. Distribute that 7, collect your like terms, isolate your variable. Now we need to check for extraneous solutions. Is that solution that we found, is that going to cause us any problems? What happens when you substitute a 2 for x back up in your original equation? Well, unfortunately, it will give us a divide by 0. Because 2 minus 2 is 0, so this is going to end up leaving us with an undefined equation. Therefore, x is equal to 2 is not a solution. In fact, there is no solution. So we write the solution set, which is the empty set, and we also write that 2 is extraneous. This example is not quite as straightforward. It's a little bit harder to see what the common denominator is. In fact, if you go ahead and factor your denominators, it's easier to see. So our common denominator is x plus 1 times x minus 1. We're going to take that and multiply it by everything. Now I know that's a lot of stuff there. It can be a little overwhelming, but it actually really helps to write all this down when you're just getting used to this. So starting over there on the left, we see we have x plus 1's. 1's in the numerator, 1's in the denominator. We can cancel those out. Moving over to the right-hand side, we have an x plus 1 that will factor and an x minus 1 that will factor. So now we need to figure out what we've got left, and now we need to solve that. And so we're going to have some foiling to do. We're going to FOIL 4x plus 1 times x minus 1 on the left. On the right, we're going to FOIL the x plus 1 times the x minus 1, and then we'll distribute the 3 into that. Then we need to collect all our like terms. And since this is a quadratic, we're going to collect everything onto one side, leaving the other side 0. Solve this as you would a normal quadratic. You can use whatever technique you want. I'll use factoring, and we end up with two solutions, a -2 and 5, and if you check them in the original equation to make sure that you're not going to get any divide by 0, you'll see that both of them end up being legitimate solutions. One more example, and this time I'm going to show you a much easier way to solve when you have a certain situation. And that situation is that if you have a single term on each side of the equation, then we can treat this as a proportion. And if you remember way back when you studied proportions, there is a property of proportions that says that the cross products are equal. So we're going to multiply, we're going to create our cross products and set them equal to each other. So 2 times x minus 1 is equal to 1 times x squared minus x. Those are the cross products. From there, it's a matter of distributing, collecting all your terms onto one side and a 0 on the other side because this is a quadratic, so we'll solve it like a quadratic. You can use the quadratic formula if you want. I find factoring to be easier, and this one easily factors. This leaves us with two solutions. Now you'll want to try both of them in the original equation, and when you do, you'll find that when x is equal to 1, we end up with a divide by 0. So that makes 1 an extraneous solution. So we really only have one solution, x is equal to 2, and we call 1 an extraneous solution. All right, final example. This is a practical application. Let's say that we've got a car that's parked and it's going to start moving, and so the equation that gives its velocity or speed in miles per hour and time since the car started moving is the equation that you see there. V is equal to 50t over t plus 5. So we're asked to find the number of seconds that it takes the velocity to get up to 25 miles an hour. So we want to know what's happening with t when v is 25. So let's set that up, substitute 25 in for v. Now we see that we have an equation containing a rational expression, and we can use actually the idea of cross products, or we can simply clear fractions by multiplying everything by the common denominator, which is t plus 5. We end up with 25t plus 125 is equal to 50t. We're going to collect our like terms. We're going to solve. So this t is telling us that it takes 5 seconds to get to 25 miles an hour. All right, good idea if you go off and get some practice in solving these equations that contain rational expressions. And don't forget, if you are a little shaky on using fractions, then you might want to review them as well.